generate electric power using a lemon. When you do that, you get what's called direct current. Last time I showed you another possibility. That involved using a simple coil of wire and a magnet. When you generate power this way, the current runs back and forth or up and down, and it's called alternating current. And this is the way nearly all power, electrical power, is generated. The best way of doing it is not to move the coil back and forth, but to make it spin around steadily like that in the magnetic field. And that is the way virtually all electric power is really generated. But of course, generating the power that way requires energy to spin the coil against the magnetic forces and drive the current around. That's usually done using a heat engine, a gas turbine, which is fired by a fossil fuel like oil or coal or gas, or by a nuclear reactor, or even by water in a hydroelectric generator. I wanted to show you how to build one of these in case you're ever stranded on a desert island and have to reconstruct civilization from scratch. So I had a simple one made up for you. This is a water wheel, which goes around like that when there's water running on it. And when it goes around, it turns a coil, much like that one over there, between the poles of this permanent magnet. The electrical output of the generator comes out on that oscilloscope, which is simply a device for showing the voltage. As long as the trace on the oscilloscope is going across horizontally, nothing is happening. But when we start generating electric power, it will start going up and down like this. Okay, so when you see that going up and down, you know that we're generating electricity. And all I have to do to generate electricity is to turn on the water. All right, are you ready for this? You better get out your umbrellas in the first few rows. Here we go. And there it is, hydroelectric power.
Okay, so how's current generated? You get a loop of wire, and then you just spin it inside a constant magnetic field. All right, so that's what we do. So by what means do we actually spin the coil? By mechanical means. Running water, pressurized steam, wind, and that's how it is done. All right, so how does spinning the wire, coil and wire in a constant magnetic field generate electromotive force? All right, let's focus on that one. All right. Okay, so the electromotive force, now we're going to be focusing on the mathematics of it slightly. All right, so let's focus on that term. Okay, so you got your coil over here. Notice that the coil is being spun in this direction. So it's on a shaft, and then you just spin it in this direction. How fast you spin it is going to be omega. Omega, you can look at it in terms of angular speed, or you can look at it in terms of angular frequency in this case. All right, in reality, physics books make a big distinction between the same thing. Okay, so I don't care how you look at it, it means the same thing. All right, so you got your regular frequency, number of cycles per second. So this becomes angular frequency, which is the same as angular speed. So which means how fast you spin this thing. Okay. Take a look at this term. All right, so this is the magnetic field intercepted by this area. Notice that the magnetic field and the area vectors are not lined up. Okay, so there's going to be an angle in between. So the amount of magnetic field intercepted by this area as a dot notation means the following. So the angle is going to matter in this case. All right, so flux is B dot A. All right, so that's the dot product that you're looking at. So if you're looking at it from this perspective, B dot A can be expressed in terms of a scalar, so it means the cosine of the angle in between is going to matter. All right, so I want you to notice that when you are actually spinning this thing in this direction, you keep changing the angle over here. Okay, so the area, size of the area remains the same. Okay, so which means that in terms of a vector, the size is going to remain the same. The strength of the magnetic field is also going to remain the same. The only thing which is changing when you spin this thing is the area which is exposed to the magnetic field that needs to be expressed in terms of an angle. So that's what's changing whenever you do that. Okay, so that's what's being illustrated here. So I'm going to take you through this step by step. All right, so the first expression says, this section says, change of flux is what generates the electromotive force. And then the expression over here is going to give you the meaning of flux. Okay, all of a sudden you notice that the flux has actually three variables. One of them is the strength of the magnetic field within the loop. The area is a variable. And how much of this area is related to how much of the flux is going to be intercepted is going to depend on the angle. All right. So you got three variables. You got the angle, you got the area, intercepting area, and the amount of magnetic field intercepted by that area. All right, so you got three things. All right, this angle that you're looking at is going to vary depending upon how fast you're spinning this. All right, so the angular frequency can be expressed in terms of the angular velocity, and that's what we do. So this angle is going to be expressed in terms of how fast the angle is changing within this time period, and all of a sudden you end up getting this expression. All right, we're using deltas. This is initially, you got a delta here, you got a delta here. This lecture was initially prepared for college physics students. That's algebra and trait-based physics. For you guys, this delta becomes even smaller, so just imagine that these are d's, which means that the intervals, time intervals, are much shorter. So this turns into a derivative. All right, guys, what is the derivative of cosine omega t? Derivative of cosine omega t is going to be, all right, so we got to express that on the side. All right, so when you take the derivative of cosine omega t, what do you end up getting? This is going to be negative omega sine omega t, right? That's what you end up getting in essence. All right, so let me illustrate that here. So when you take the derivative of this expression, number one, you're going to pull a negative when this turns into a sine. Yeah, let's just get rid of the colors. All right, so this turns into a sine. And obviously, when this turns into a sine, there's going to be a negative here. So that negative is going to get rid of that negative. And then when you take the derivative of this, you will have omega. So the omega is going to be placed right there. All right, so in terms of sines and cosines, okay, so I'm going to end up using the side for a mathematical discussion. Got the sines and cosines of waves. All right, so here's a sine wave for you. This is one single wavelength. This is a second wavelength. This will be the amplitude of this wave. Okay, so this is your y-axis. This is your x-axis. Okay, guys, this is just a general mathematical argument that I'm trying to show you. All right, so this could be mathematically represented in terms of a sine wave. All right, and I don't know if I want to use this. Okay, just keep it like that. That's fine in terms of mathematical expression. Okay, what I'm getting at is here's the amplitude. Amplitude is the maximum height of a wave that you're looking at. And so this could be represented as a sine wave. So what's happening on the x direction is going to change what's happening on the y direction. So the projection changes as a sine wave that you're looking at. All right, so same sort of expression is taking place here. So you got your sine wave over here. And here's the sine wave that you're describing. It's going up and down. All right, and as a function of time, of course, you got the expression omega. In reality, this is the theta axis, because this becomes theta. But let's ignore that one. I'm being a little bit too picky. What I'm interested in is this expression up front. That's the reason why I've been just giving you the mathematics. What's in front of sine or cosine is known as the amplitude. This represents the maximum height of this. All right. So the expression that you're looking at, you would say, hey, this is the maximum voltage or electromotive force that it can have. All right, so just by mathematical means, in front of sine omega t becomes the maximum amplitude of this voltage. So, which means that this is the maximum voltage value that the circuit is going to have. That's what it means. All right, so this NBA omega, so you got the National Basketball Association omega, is going to represent the maximum voltage value that you can generate. All right, so that's the meaning of it. So as a result, the electromotive force is going to be expressed like that. All right, so let's get out of here. Okay, so what do we have? How does spinning the wire coil in a constant magnetic field generate electromotive force? Okay, guys, once again, I'm going to express these in terms of the math equations. When you have these questions on the test, I try to stay away from the formulas. Just try to explain things as well as you can. What's generating the electromotive force is you're changing the strength of the magnetic field inside the loop, okay, or you're just simply changing the flux. All right, so what I'm expressing mathematically, mathematical expressions usually is just a summary statement. So the only thing I'm doing is I'm just changing the, okay, so I'm just gonna move this up. I'm just changing the magnetic flux. Changing magnetic flux is what generates the electromotive force. That's it. All right, so by spinning the coil, what I'm doing is the magnetic field is gonna be constant. I'm just varying the exposed surface area. I'm gonna use the vector notations, but in reality, what I'm doing is I'm being real picky right here. I think what I'm doing is I'm just changing the angle between the N and A. All right, so I keep changing vector notations. All right, so everything that I described can be mathematically expressed in this fashion. And so this is a symbolic representation of what we were discussing. Of course, in the conceptual section of the test, I want you guys to kind of reason and explain. Okay, so try to stay away from equations. Okay, so what's the relationship between the maximum electromotive force and the frequency of the spin? Okay, so the maximum electromotive force In this case, I'm going to get back to this one. All right, so number one, you end up getting a sine or a cosine wave. All right, so which means that your maximum electromotive force is going to keep varying in time. All right, so I'm just going to, this is what we're looking at. This is the electromotive force. That's your voltage. This is your time. And okay. And this is the maximum value that you can have. Okay, cool. All right, so the question is, this maximum value, what does that depend on? It depends on the number of turns. All right, so I'll do a visual for you. All right, so this is your coil. It's going to have a cross-sectional area. So you got your number of turns. And there's going to be a magnetic field accepted by this. This is what to be here across this area. Times how fast you're spinning this thing. Okay, so that's a nice visual representation of it. So that's angular speed could be expressed in terms of linear frequency. That's your 60 times 60 hertz current. All right, so this is usually 60 hertz. Okay, so that's what we end up getting. All right, I don't know if you guys remember this, but there's RMS values, root mean square values. So let's have a little bit of a discussion regarding that. Okay, so this portion requires a little bit of participation. All right, for those of us who have to pay bills, if you're renting a place or whatever, more than likely you have to pay a certain amount of money for the electricity that you're getting. Okay, so here's the problem though. Okay, this is what you end up getting from the socket. All right, you end up getting voltage from the socket. What's electricity which is being fed into the socket is alternating current. And what's driving the current is the voltage. Notice that the voltage goes up and down as a sine wave, which means that the current that the voltage drives. So this is the voltage. This is the resistance of the wires in your home. So this is the amount of current that you end up getting out of it. Okay, so the voltage is what drives current. So this is what the voltage does. It goes up and down. The current does the same thing. All right, so you got a maximum amount of current that you can generate out of a maximum amount of voltage that you can generate. Okay, now we got a slight problem. The problem that we end up generating is, guys, what is the average amount of voltage you get from the socket though? Zero. It's your maximum. It's going to be zero. Very good. Who said that?
Ian.
Ian, the amount of voltage that you get is going to be zero. Give yourself 5 points. So what's the amount of, the average amount of voltage you get is zero. So what's the amount? Shit. What is the average amount of current you get from a socket, if that's the case?
Zero.
Okay, on average you get zero voltage. On average you get zero current from a socket, right? Okay, so if that's the case, what are we paying for, basically? All right, I mean, why not just call up the power company and say, you know, I got a bill, but I don't understand what for, because on average I'm not getting anything from you guys. But they give you something and they take it away. All right.
They charge you for both.
I'm sorry, what?
You said then they charge you for both.
Well, on average, I'm not getting anything. So why not, on average, I should be giving him the same stuff that I'm getting. Just give him a $100 bill and take it back.
I'm going to try that next month.
No, if you want to, just call him up and check to see what's going on. All right, guys. I mean, if you are like me, if you like harassing people from time to time, all right, just call up the power company and just explain what it is that you're paying for. All right. On average, I'm getting zero voltage, which means that on average, I'm getting zero current, electricity. All right. So why should I don't understand what I'm paying for. And then they will just pass you on to an engineer, and then most likely I'm going to be talking to a person like you, which is fine because you guys are kind of like art students, easily confused. So eventually you will get passed around for a while until they find someone who knows what's going on. They're not charging you for the current or the voltage. What is it that they're charging you? They're charging you for the power. Oh my God. And all of a sudden you go, oh, somebody usually knows what's going on. All right, guys.